And very stringent optic requirements have a series of requirements which are very stringent, and this is why you need to use a compensation scheme for the solenoid. The integral longitudinal field seen by the electrons and positrons needs to be 0. The vertical emittance blow-up needs to be within our budget. Our budget is of the order of 1 picometer, so it needs to be less than half a picometer for all IPs. Any dispersion bumps need to close locally, and the final focus elements need to be at a very low longitudinal field. So the total integral field where the final focus elements can operate needs to be less than 50 millitesla meters. So to actually make you understand a bit what we're talking about, I'm going to give you an example, which happens to be the baseline solution for FCCE. This is what we've come up with. What are the requirements? L star of 2.2 meters. This is defined by optics. So we have all the space in the world between 0 and 2.2 meters to put all our elements. There needs to be a screening solenoid that makes sure that the final focus quadruples do not see the detector solenoid field. So this actually starts at 2 meters. The luminometer needs to be as back as possible from the IP to get a decent rate. So it would go as back as allowing this element here, which is a compensating solenoid, and this is what defines a 0 integrated field between the IP and infinity. So the shorter you can make the compensating solenoid, the further away you can push the luminometer, the higher the rate of your luminometer, and the better it is. So I want to stress here that unlike linear colliders that have actually were not brave enough, we are facing the challenge of final focus quadruples inside the detector. We're not trying to put them outside. This increases the performance, of course, for us a lot. So if I zoom, of course, in the area of 2.2 meters, these are my final focus quadruples. Okay, so this was the MDI session today. 5 talks. And please note that the distance between the last talk and the parallel session was not really, the summary was not really so big, so I had to do things in a hurry. First talk was by Yasushi Arimoto. We invited him to make sure that we talk about the machine which is already built. So this is experience from a machine which is in many ways similar to what we tried to do. This is the interaction region of belt 2. It should have been called the VVC system. Very, very complicated, as you will see. Already in this plot, you see that there is different sets of magnets, quadruple magnets, compensation solenoids, and a series of other compensating magnets too. The compensating solenoids called cancel magnets. What the cancel magnets do is they cancel the leak field of one quadrupole to its neighbor because they're sitting very close together, and they consist of a series of B3, B4, B5, B6 magnets. This is all, when I think about it, I get very dizzy from the number of different machine elements. This is how they look like, the cancel magnets. So here I open a parenthesis to actually say that in our case, things are slightly simpler because both of our beams are very strongly coupled together. Actually, we have exactly the same energy for both beams. This can simplify the design considerably. So for FCCE at least, the quadruple design is such that any cancel magnets, as they were called in Super KEK-B, are actually incorporated in the quadruples themselves. So it's only 1 unit instead of the 10 units that you've seen before. Okay, close parenthesis. Compensation solenoids. This is what the field looks like if you don't have any compensation. You need to make sure that the integral of this guy is 0. You introduce compensating solenoids so that the integral of the field is actually 0. Please note a big difference between us and Super KEK-B. This first quadruple element is inside the magnetic field. This is a rather large field. This is simply from the fact that the L star of this machine is 0.8 meters, and in our case it's 2.2. So in the case of Super KEK-B, there's simply not enough space to actually do everything before the final focus quadruple as we try to do. Compensation solenoids. This is how they look like. Operation current is reasonable. Magnets have been measured. The quality of the quadrupole magnets is good enough. Their tolerances was less than 10 units. In our case, the tolerance is less than 1 unit. And you still see that there is a specific magnet here, QC2RE, that has multiple components of beta 3 of 20 units and of the octopole component of 7 units. So there are a few magnets with rather high multipoles. This is how the beast looks like. 2 cryostats sitting opposite each other, total weight 4 tons. The measuring campaign, of course, gave some unexpected profile for some numbers. That's reasonable. It happens all the time. An effort has been made to actually find the magnetic center of all the elements of the final focus quadrupoles. And what was found was that the maximum offset from the beam is 700 microns, which I personally thought was a very large number. But if you think about how big the system is, then maybe it's reasonable. This is a summary of the first speaker. Effectively, what I want to say is that the scheme comprises 55 magnetic elements. This is a huge number. It's very, very, very complicated. I would hope that we will be able to actually make something a bit simpler than that. I go to the second talk by Shabai, overview of the MDI, of CEPC. So here is an outlook of how the system looks like. This is very similar to the baseline plot that I showed you from FCCEE, apart from the fact that this angle here is 120 millirad, if my calculations are correct. This is the famous cosine theta of 993. So they're giving themselves slightly 20% more space than we have. And the number of elements is very similar. They need to find a way to correct the crosstalk between their superconducting quadrupoles, and they have done so. And the overall result is that the multiples that they're left with is of the order of 3 units, which is not a bad result. As I said, for FCCE, we're aiming for less than 1 unit. The current, the gradient they're using is 140 Tesla per meter. We have limited ourselves to 100, but it's not a big difference. Solenoid compensation looks the same as the baseline design I showed you before. This is the field without compensation. With the compensation, it looks exactly, well, the integral is exactly 0. What is the emittance growth? Turns out it is of the order of 3 picometers. And I remind you, I have a couple of slides at the end about this because I think this is an important point. The budget is 1, so they're actually exceeding the budget by 300%. They have done a mask design, which you're going to see in a minute in a further talk, to make sure that no photons reach the region, the interaction region. And they've looked into all the different sorts of backgrounds. Some of these backgrounds are going to be discussed in a minute in the later talk. They have a collimator design. You see a series of 4 collimators for the Higgs, and they also have the same actually collimators for the Z, and they say everything works fine. They even have some ideas about how to assemble the whole business. They start by putting the calorimeters, then pushing the 2 compensating solenoids close, and then pushing the calorimeters back until they touch. I guess this is like a first idea of how this is going to be done. This is how it looks like. So this is the cryostat that has the compensating solenoids and the final focus quadrupoles, and this is the luminometer, if I'm not mistaken. What I can see already in this design is that they've put in front of this the bellows and all this engineering stuff which is needed. This is not a very good idea for the luminometer. I think the luminometer guys are going to scream when they see this. We have tried to actually fit all these things behind with some relative success, as you will see. Again, the assembly, they've thought about how to go from a single beam pipe to a double beam pipe, putting beam position monitors, et cetera, having the water cooling. This is the summary. And I move to the third talk. How am I doing with time? Okay, detector solenoid compensation scheme at FCC-EE. So this is the baseline design which we've seen before. And you see, so in the engineering world, you need to actually fit these elements somewhere behind the luminometer. These elements are the higher order mode cooler, then the BPMs, and then some kind of bellows and vacuum connection. Okay, so these elements in the original baseline design actually fit inside the cryostat, which is of course a bit awkward. Calculation of emittance blow up is 0.3 picometers, which is fine. The question is, can we do better than this? Sergey has done a very detailed study of studying different sizes of compensation lengths and seeing what is the emittance blow up and deciding on what we want to use. And he comes to the new design. He says, for the new design, where they reduce the main solenoid field, we don't want to do that. We can also change the placement of the first finer focus quadrupole. We don't want to do that either. We don't want to put it further back. Or we can increase the opening angle from 100 to 140 millirad. We don't want to do this either. So we left with some more complicated schemes, which is a cylindrical compensation solenoid. Instead of having one compensation solenoid, you actually have two individual ones. That is beneficial for the emittance blow up, but creates other problems. You can put an individual cylindrical compensation solenoid, which is what we've done, or you can have an elliptical compensating solenoid. So this is the new design that actually tries to put all these engineering components which are needed behind the luminometer and before the screening solenoid, that it leaves less space for this thing to do its job properly, and it creates other problems. One of the problems that it creates is that it introduces skew components that need to be absorbed. So you need to have compensating solenoids inside your solenoid to actually absorb the skew components. This is how it looks like from another view. So your field profile now looks, depending on one of the three schemes, the individual cylindrical solenoids or the cylindrical solenoid for both beams or the elliptical. So number one, you see already that the field actually has a very high value at 2.2 meters. So this is not compatible with the scheme of lambda star of L star equal 2.2 meters. But of course, 3 is actually a bit better. So this would be his preferred solution. And if he does the calculation for the vertical emittance, he sees that the vertical emittance in this solution 3 is actually very good. There's no blow up. This is the parameters. But what I can see is already that dispersion does not close. And this is actually very bad because you need to, ideally you need to close the dispersion pump locally in the vicinity of the interaction region, not have it leak everywhere in the machine. So this is his summary. And I move to the fourth talk with the radiation backgrounds from the CEPC by Hongpo Chu. So this is his first slide. So effectively he's dealing with these 4 different backgrounds. Pair production is when you get pairs from the hard photons in the interaction region. This is the heat density seen by the detector. It's not clear to me the color scheme, what is actually bad and what is okay, but he says that everything is fine. The number of hits per bounce crossing seems to be very reasonable. It's of the order of 2 in the innermost layer of the vertex detector, which is a good number. There is 2 collimator designs that actually reduce by 1 order of magnitude or 2 orders of magnitude the rate. And there is a design for a mask to get rid of the synchro radiation. So this will be difficult to see, but effectively what you see here is this cloud is photons deflected at this point and actually creating havoc. If you design a mask that is not symmetric from any point of view. It's only 0.6 millimeters high. It's a very, very small thing, and 4 centimeters long. Then what you do, you have put 3 masks, one here, second here, and the third here. You reduce the huge background you see there, and from 40,000 photons, you go down to 80. This is his summary. Is this the last talk, or maybe the one before last? The challenges for the mechanical design point of view. First slide, we need to design cryostat, you need to design flanges, bellows, BPMs, etc. So this is the design promoted by Sergey, which is actually is the design. It's not the baseline design, if you like. It's the one where the this engineering components are actually outside the cryostat. So with a very short cryostat. So these are the you'll see in the next plot. He has a design. There is a conceptual design for the beam pipe, which is very good. This is not the beam pipe that goes at the interaction region, but is the beam pipe that goes when the single beam pipe splits in 2 beam pipes. Okay, this is water cooled. It's made out of stainless steel and other components and plastic. Outer diameter is 38 millimeter, which is fine. Inner diameter is 30, as requested. For the beryllium beam pipe, no study has been done, but the hope is that we would not even need to cool it for a meter or so, and then we try and remove all the heating at the end. This is how this design of the 3-layer beam pipe looks like. And they also have a design for the remote flange. It's something that would actually, you be able to hit a key and actually lock this thing remotely somehow. So you are sitting 1 meter away, and you would be able to actually remotely lock this device. This is his summary. And before I finish, I want to actually make, as I promised at the beginning, a last point. It has to do with the emittance blow-up. 2 Tesla versus 3 Tesla field. So I have some good news and some bad news for you. Good news is that the emittance blow-up is a strong function of beam energy. It actually goes as the beam energy to the third, so you don't need to worry. You only need to worry about 45 GeV. At 80 GeV, the problem reduces by a factor of 6 already, and it becomes negligible. So the only point that you need to pay attention, the one you might need to reduce the field of your detector, is at 45 GeV. And now the bad news. The emittance blow-up is a strong function of detector solenoid field. How strong function? It actually goes to the 5th power. Okay? It's a bit of a problem. So going from 2 Tesla to 3 Tesla, you increase your emittance blow-up by a factor of 8. So if the emittance blow-up from 2 IPs is, as we have in approximately in FCC EE, of the order of 0.4 at 2 Tesla, if you go to 3 Tesla, you go to 3 picometers. Your emittance budget is 1, so you're 300% more. So luminosity will reduce by a factor square root of 3 for the same statistical accuracy, and you need to run 1.7 times longer. So to my mind, it's not really worth, presumably, you never actually going to be able to recover this function, this 1.7 factor by a much better detector going to 3 Tesla. Anyway, so these are my conclusions. So it was a nice session showing that MDI design for both the CPC and FCCE are coming of age. We're now actually dealing with even engineering problems, not only conceptual problems. Backgrounds are important, but can be mitigated. I didn't hear anything about any potential showstopper regarding backgrounds. There's still a lot of work to be done, mainly on the magnetic design. To my mind, the most important questions are, can an elliptical compensating solenoid work, as suggested by Sergey? I don't know. Can the baseline design be implemented? You know, the baseline design works very well, but engineering-wise it's difficult because you need to fit inside a few elements inside your cryostat. What exactly are the engineering challenges? I'm not even sure. Is it the accuracy of construction? Is it the force management? Is it the difficulty in assembly and disassembly of the machine? I don't have a feeling for that. And finally, going from 2 Tesla to 3 Tesla at the Z will cost the experiments nearly a factor of 2 in statistics. I believe that this more than compensates the loss of detector performance, which cannot be more than order 5%. And I concluded that. Thank you very much.
Okay, thank you, Mike, for this nice talk. Questions?
If you go to the second point in your conclusion, backgrounds are important but can be mitigated. Okay? I mean, when you put your quadrupoles inside your detectors, etc., I imagine for the FCC, is there any full simulation of the whole detector, the whole system, or just fast simulation? And all the results that were presented up to now are based on what? On fast simulation or real simulation?
I think I will leave somebody else to answer this. I cannot answer you this question.
Just wait a second, wait a second.
Specifically for beam gas, I will do a presentation tomorrow. However, yes, you will need a full simulation in every case.
Okay, other questions or comments? No? See, now we are on time. Well, thank you very much, Mike.